video lecture, we shall discuss the effect of isotopic substitution in a rotating diatomic molecule and the rigid rotor. Here, we are going to discuss how the rotational energy levels and the spectrum of any diatomic molecule change when any one of the atoms is replaced by its isotope. An atom having same atomic number and different mass number is called an isotope. In the rotational spectra of any diatomic molecule, if you substitute the atom by its isotope, then there will be change in the spectral lines. In this technique, one can find out the mass of the isotope and the abundance of the isotope from the intensity of the spectral lines. If we compare the microwave spectrum after substituting the isotopes with the original spectrum and compare the intensities, one can find out the abundance of the isotopes. The presence of isotope in a rotating molecule changes its reduced mass. And of course, we know that I equals mu r squared. Mu stands for reduced mass. So since mass changes, the reduced mass also will change. The changing moment of inertia I is inversely proportional to the rotating constant. So rotational constant, as I changes and B also should change, and both are inversely proportional. And of course, we know that I equals mu r squared, and we are going to replace the isotope, heavier mass. So mu will increase. If mu increases, I also will increase. If I increases, B, the rotational constant, will decrease. For any isotope, the rotational constant will have lower value. So the separation in wave number also changes as del mu bar, which is equal to 2B. When an isotope replaces an atom in a molecule, the rotational spectra of the molecule change. This change in frequency separation of a rotational spectrum due to the presence of an isotope in the diatomic molecule is known as isotopic effect. When a rotating molecule is substituted by its isotope, the interatomic distance remains the same, but mass will be changed, and this leads to a change in moment of inertia. The isotopic forms of any same molecule are indicated as 1 and 2. So we are going to have 1 and 2 as two indices. Both represent different isotopic forms. We know that the frequency of the absorption line in a rotating molecule is given by mu bar, which is equal to 2bj. J is the rotational quantum number, B is the rotational constant. The frequency of the first isotopic form is given by mu1 bar, which is equal to 2b1j. And we know that B equals H divided by 8 pi squared IC. So substituting the value for B, here it is B1, we have 2 times H divided by 8 pi squared I1C times J. So nu1, which is equal to Hj divided by 4 pi squared I1C, equation 1.22. Now frequency of the second isotopic form, nu2 bar, which is equal to 2b2j 2 times H divided by 8 pi squared I2C times J. So nu2 bar equal to Hj divided by 4 pi squared I2C. So we can get the change in wave number, which can be calculated by equation 1.22 minus equation 1.23 we have. So del nu bar, which is equal to Hj divided by 4 pi squared I1C minus Hj divided by 4 pi squared I2C. Taking the common terms out, we will have in bracket 1 by I1 minus 1 by I2. Now just to pull I1 out from the bracket of equation 1.22, we get this equation. So we have pulled I1 in the denominator out. So, but we know that already B equals H divided by 8 pi squared IC. So this can be written as 2B, because we can write 8 as 2 times 4. So we can write this as 2bj 1 minus I1 by I2. I1 minus I1 divided by I2 is nothing but rho. So this can be written as 2bj1 minus rho squared. So del nu bar is directly proportional to J. It implies that the change in wave number in the rotational diatomic molecule is directly proportional to the total rotational quantum number J. The effect of isotopic substitution in carbon monoxide, CO. So now here C12 is replaced by its isotope C13. Here it is a diatomic molecule. When C12 is substituted by C13 isotope, the rotational spectrum is shifted. We are going to find out. By measuring B and B dash values, B stands for the rotational constant while observing C12, B dash stands for the rotational constant, B dash is nothing but rotational constant while getting the spectra of C13 isotope. It's possible to determine precisely the atomic weight of atoms. C13 atomic weight was estimated as 13.007, which is within very low percentage, 0.02% of the best value obtained by other methods. Effect of isotopic substitution. When a particular atom in a molecule is replaced by its isotope, the resulting substance is chemically identical with the original. There is no appreciable changes in the internuclear distance, so the bond length will never change when you are going to substitute an isotope on isotopic substitution. But the moment of inertia changes as mass changes, and hence the value B, the rotational constant also will change. Now look over here, we have C12O is here, and O has a mass M1, C12 has mass M2, and they are connected with some bond length, and here it is O, and here it is C13. The bond length remains the same, whereas C13 has a heavier mass. Here bond length remains the same, whereas the mass of the diatomic molecule alone changes. Now we are going to compare the rotational constants of the molecules with and without the isotopes. Now here it is C12 O16, here it is C13 O16. Let us see. Now you just find out the moment of inertia for the first one without isotope. So I equals mu r squared. Now with isotope, as we said, that is a heavier atom, and the mu, the reduced constant, the reduced mass changes. So we have I dash, which is equal to mu dash r squared. And we know that B equals h divided by 8 pi squared IC, and B dash equal to h divided by 8 pi squared I dash C. And divide this by this will give us B divided by B dash, which is equal to h divided by 8 pi squared IC divided by h divided by 8 pi squared I prime C. Now simplifying, we will get, and cancelling the same terms, we will get B divided by B prime, which is equal to I divided by I prime. And of course we know that I equals mu prime r squared. So here it is divided by mu r squared, and r squared will get cancelled, and we have mu dash by mu. So it implies that as we said that mu dash is heavier, is greater than mu, and we know that since mu dash is greater value than mu, and B value should be greater than that of B dash. I repeat, here mu prime is greater than mu. Since mu prime is greater than mu, and B must be greater than B prime. So it implies that the value of rotational constant is found to be less with the substitution of isotope in the rotating diatomic molecules. When a particular atom in a molecule is replaced by its isotope, the resulting substance is chemically identical with the original. There is no appreciable changes in the internuclear distances on isotopic substitution, but the mass corresponding the moment of inertia, and hence the value of rotational constant changes. When the increase in isotope mass, its rotational constant decreases. Just now we have seen, if the substitution per molecule is designated with B prime, then B is greater than that of B prime. So B prime stands for the rotational constant for the molecule when isotope is included. This change is reflected in the rotational energy level of the molecule. The spectrum of the heavier species will show a smaller separation between the lines, which is nothing but 2B prime, than the lighter one, which is nothing but B. Observation of this decreased separation has led to the evaluation of precise atomic weight. Knowing the value of B, B prime, mu, mu prime, the mass of the isotope can be easily determined. On changing from without the isotope and with isotope, that is C12 to C13, in CO, atomic mass increases and B decreases. And of course, we know that B is directly proportional to 1 by I, moment of inertia. So the energy of the levels become. So this is the energy of without isotope of a diatomic molecule, carbon monoxide, and this is with isotope. So this is C12 and this is C13O. And we can, this is the upper one is energy levels, and here this is represented as spectrum. So this is the energy spectrum, and this is nothing but energy levels of a rotating diatomic molecule, CO, carbon monoxide. Now look at the energy levels. This represents J values. When J equal to 0 and J equal to 1 and J equal to 2, there is no change in energy level. You just look over here, almost it is the same. There is no change in energy level. Whereas when J increases, you just point out when J increases, the separation between these two lines decreases. See here, the separation between these two lines decreases here, right hand side. You just compare this line and this line. And when J increases, say J equals 5 and J equal to 6, the separation decreases. It's very important information. The energy and the energy gap between rotation energy levels decrease as the isotope mass increases, and is predominant with the higher values of J. And this can be denoted, see exactly 2B, here it is 4B, and there's a small separation, here small separation, and 8B also, and we have 12B, there's a lot of separation. So when J increases, it's predominant. The separation is predominant, one. And second one is, here it is, but it is very less. Here it is almost same, here it is very less. Isotopic effect on rotational spectroscopy. One can find out the mass of the isotope of any unknown element. If we compare the microwave spectrum, after substituting the isotopes with the original spectrum and compare the intensities, one can find out the abundance of the isotopes. The effect of isotopic substitution on rotational spectra can be used to identify isotopic species in a sample and to determine atomic weights. The isotopic shift of the rotational lines is proportional to the ratio of the reduced mass, and these rotational lines may be observed within the far infrared region still, because the rotational spectra can be used for the determination of bond lengths in molecules, methods of optical molecular spectroscopy right from 1929. The energy and therefore the energy gap between two rotational energy levels of a molecule depend on the isotopic mass of the atoms. Also, the energy and the energy gap of a rigid diatomic molecule are reduced with the increasing mass of isotope. The separation of the levels for the heavier isotopes will be smaller than those of the corresponding levels of the lighter isotope. It implies that the spectral lines will be closer. So these are the inference that we can learn from substitution, isotope substitution in a diatomic molecule. Now we will go into non-rigid rotor. The assumption of a rigid bond in a diatomic molecule is only an approximation. So we approximated when we studied the rigid bond. The bond length is not, actually speaking, the bond length is not rigid. It is represented by a string-like structure. It is an elastic one. The bond of molecules is stretched while they are in rotation. Hence the bond length of molecules increases with the increase in the velocity of rotation. The separation between successive lines in the spectrum, that is B, decreases steadily with increasing J values. The reason for this decrease may be seen if we calculate internuclear distances from B values. That is, as B decreases, the bond length increases. Hence, the bond length increases with J. It reflects the fact that more quickly A diatomic molecule rotates, the greater the centrifugal force tending to move the atoms apart. As J increases, the internuclear distance also increases. As we can conclude that bond length is not rigid, but the bond is elastic. If the bond is elastic, the atoms will compress and stretch. It results the vibration of molecules when J increases, other than the rotation. So there will be a vibration motion in addition to the rotation of molecules. When the bond is elastic, a molecule may have vibration energy too. A bond will stretch and compress periodically with a certain fundamental frequency. Moreover, they will have weak bonds and stronger bonds, depending on the elasticity of the bond length. It depends on the masses of the atoms and the elasticity, which is nothing but force constant of the bond. If the motion is simple harmonic, it's a very good approximation here. The force constant is given by K equals 4 pi squared omega bar squared c squared mu. Here omega bar is nothing but vibrational frequency measured in centimeter power minus 1. The variation of B with J is determined by the force constant. The weaker the bond, the more readily it will distort under centrifugal forces. The quantities R and B vary during a vibration. When these quantities are measured by microwave techniques, many hundreds of vibrations, and hence the measured value is an average. However, from the equation B, we have B equals h divided by 8 pi squared IC, and I can be replaced by mu r squared. The centrifugal force arising from rotation distorts the molecule, opening out the bond angles and stretching bonds slightly. The effect is to increase the moment of inertia of the molecule and hence to decrease its rotational constant. Experimentally, it is found that the separation between the adjacent lines decreases steadily with increasing J. The reason for the decrease is obviously due to the decrease in the B value. All bonds are elastic to a certain extent, and the bond is not rigid as we assumed in rigid rotor. Therefore, for a correct treatment, one has to use the complete Hamiltonian of a non-rigid rotor. The solution of the Schrödinger equation gives the following energy expression of the energy levels of the non-rigid rotator, and is given by this. So the second term says about the correction. The second term, and of course we know about the first term very well. This occurs due to rigid rotor. The second term is the correction because of the vibration as well rotation. We have both. Both will occur at the same time due to the elastic bond of the two molecules. So now changing into wave number, we will have to divide by Hc. So we will have and divide by Hc on right hand side, and left hand side also it should be divided by Hc. So we have this term equation 1.30, and we know that B equals h divided by 8 pi squared IC. So this term can be replaced by B, and we are going to substitute, instead of this term we are going to substitute this one by D. D equals h cube divided by 32 pi to the power 4 I squared R squared Kc, and this equation 1.30 becomes 1.31. The new J bar, which is equal to B J plus 1 minus D J squared J plus 1, where we know that B is the rotational constant, J is the rotational quantum number, we know already, and D stands for centrifugal distortion constant. From the above equation, it is evident that the effect of centrifugal distortion is more for those molecules having small moment of inertia and the small force constant. See, because they are in the denominator, if they are very, very small, and this will have more effect. In a given molecule, the effect of the centrifugal distortion is to decrease the rotational energy. However, it increases rapidly for higher rotational states. For a diatomic molecule, D is related to B and the fundamental vibration frequency nu bar of the molecule by this relation. So D equals 4B cube divided by nu bar squared. And we know that the expression for the fundamental frequency of vibration is given by this one. So nu bar, which is equal to nu by C, which is equal to 1 by 2 pi C root of K by mu. where K is the force constant, mu is the reduced mass. Substituting the values of B and nu bar. So substitute the values for B and nu bar in this expression. So we have in this expression we have D equals 4 times, instead of B cube you substitute H divided by 8 pi squared IC, and here nu bar, so 1 by nu bar squared is there, so we'll have to change them, right? This becomes 4 pi squared C squared mu divided by K. Now this 4 and this 4 multiplied by 4 will give us 16, and this term can be simplified as H cube divided by 8 cube. 8 cube is nothing but 5 1 12, 5 1 2, 5 to the power 6, I cube C cube, and this 16 divided by 5 1 2 give us 32, and 5 squared and 5 to the power 6, that will give us 5 to the power 4, and of course we know that I equals mu r squared. 1 mu is here, so here it is mu cube r to the power 6, and here 1 mu is there, so that will give us mu squared r to the power 6, and remain C cube and C squared, and that will get cancelled. You have C and K is here, of course, so one can get the expression for D here. The knowledge of D gives rise to two useful information. It allows us to determine the J value of lines in an observed spectrum, and a knowledge of D enables us to determine the vibrational frequency of a diatomic molecule. See, look at the figure. Look at the expression D equals 4 beta cube divided by mu bar squared. And next figure, this figure is a symmetric representation of energy levels and the spectrum of rigid rotor as well non-rigid rotor. So we are going to compare rigid rotor as well non-rigid rotor. Already we know the rigid rotor very well and we studied earlier. Now we are going to compare the rigid rotor with non-rigid rotor. This is just for the comparison. The rigid case is also included in the figure, just for the comparison. If J value of transition is fixed from the frequencies of two lines, one can determine the constants B and D from which an estimate of the fundamental vibration frequency of the diatomic molecule may be estimated. It is noticed that it is predominant for the higher values of J. Now we shall compare. As we know that these are all the energy levels, and this is nothing but spectra of rigid and non-rigid rotors. See, we have for lower values of J. So this extreme left side, which is nothing but J values, 0, 1, 2, 3, they are all J values. And look at the energy levels. When J equals 0, J equal to 1, 2, 1, 2, they are almost same. For lower values of J, these lines for the energy levels of rigid rotor and non-rigid rotor are the same. Whereas when J increases to 5, look at J equals 5, and here it is very less. See, here it is somewhat less, and there's a small separation here, small separation. And when J increases higher values, say up to 8, the separation also becomes larger, and this separation of the same here, that is very less, and here its separation is more. So when J becomes more and more, the separation is more, whereas here the separation of non-rigid rotator, that is energy level within the non-rigid rotator level, decreases. So this is corresponding spectrum of rigid rotor, and this is non-rigid rotator. See, almost it's the same. See, here we have 2B, 4B here, 4B prime. When J value increases, see, there's a slight separation, whereas when J increases very fast, J is very high and separation is larger here. See, that's a separation. The analytic expression for the transition of the non-rigid molecule using equation 1.31. So this is equation 1.31, which is marked as red color. Now we shall find out the transition, that is absorption line, from J plus 1 to J plus 2. So this becomes from one level to another level. So what I've done is, instead of J, you substitute J plus 1. Here is J plus 1 means J plus 2. In the equation 1.31, J squared will be replaced by J plus 1 whole square. j plus 1 whole squared is replaced by j plus 2 whole squared. Now we'll have to find out the separation. We'll have to find out the separation, that is absorption line. So this is nothing but your j plus 1, so j plus 2 minus this j plus 1. So bj plus 1, wherever you find the j, you substitute j plus 1. See here, so bj plus 1, so j plus 1 becomes j plus 2. And what a minus d in sub j, you substitute j plus 1 whole square, and j plus 1 becomes j plus 2. On whole these things for j plus 2, and this is your j plus 1. So this becomes pj j plus 1 plus dj square j plus 1 whole square. Now we just separate b alone, b this side. So you are going to separate b on this side and d on that side. So equation 1.37 is obtained. So bj plus 1 j plus 2 minus bj j plus 1, and taking the minus term out, we'll have dj plus 1 whole square j plus 2 whole square minus, already my plus is there, so minus plus, so minus dj square j plus 1 whole square. Now I have pulled j plus 1 common out. So out of this bj plus 1, here also j plus 1, I have pulled bj plus 1 common out. Remaining term will be j plus 2. And here the remaining will be minus j. And minus j and plus j will get cancelled. We have 2. So this becomes 2bj plus 1. And coming here, we have minus dj plus 1 whole squared out. You just take j plus 1 square. So dj plus 1 whole squared out. So this becomes j plus 2 whole squared, and here it is minus j squared. And of course j plus 2 whole squared is nothing but j squared plus 4j plus 4 minus this j squared is here. J squared and j squared will get cancelled. 4j plus 4, you pull 4 out, so that becomes j plus 1. Already we have j plus 1 whole squared is there. Multiplying with j plus 1, that will give us j plus 1 whole cube. Here you have 4d is here. So your new j bar, which is equal to 2b j plus 1 minus 4d j plus 1 whole cube. Thus the frequency of the transition from j plus 1 to j plus 2 is given by this expression, equation 1.38. The first term is the same as the one due to rigid molecule. Suppose if there is no d, and this refers only for a rigid molecule. And the additional term gives the shift of the lines from that of the rigid molecule, which increases with j as j becomes j plus 1 whole cube. So d exists. So this is the additional term. This is for the non-rigid rotor. Okay. That is the end of the session. We'll wind up here.